Let's jump right into this explainer. Today, we're taking a look at a really fascinating engineering challenge: how we evaluate concrete's structural integrity over time. Specifically, we're going to zero in on a classic tool that engineers have leaned on for literally decades: the Schmidt rebound hammer.
So imagine you're tasked with testing a massive bridge pillar, right? Or maybe a towering skyscraper support, or even an active airfield pavement. You obviously can't just knock these structures down to see how strong they are. So how do we actually solve this non-destructive challenge? How do we look inside the material without breaking it all apart?
Here is our quick roadmap for today. First, the non-destructive challenge. Second, enter the rebound hammer. Third, exactly how the hammer works. Fourth, its variables and serious limitations. And finally, the final verdict.
All right, let's start with Section 1, the non-destructive challenge.
Traditionally, if engineers wanted a truly accurate reading of concrete strength, they'd have to physically cut cylindrical cores right out of the hardened concrete and then literally crush them in a lab. But here's the catch. This kind of destructive testing actually weakens the structural integrity across the whole cross-section of the member you're drilling into. Not to mention, if you happen to hit hidden steel rebar, cutting a clean core becomes an absolute nightmare. That's where non-destructive tests come in. They attempt to measure completely different properties, like surface hardness or the velocity of sound, so we can safely estimate the concrete's compressive strength without leaving a single scratch on it.
Moving right along to Section 2, enter the rebound hammer.
Invented way back in 1948, the Schmidt rebound hammer is basically a surface hardness test. It runs on this core principle. As concrete hardens over time, its surface hardness goes up in a way that kind of correlates with its overall strength. The classic manual hammer, which, let's be honest, looks a bit like a really heavy-duty metal flashlight, requires a solid testing anvil to calibrate it. Then you have the modern digital version. But honestly, despite the fancy digital upgrade, the mechanical physics happening inside that tubular housing are exactly the same today as they were in 1948.
Which brings us to Section 3, how the hammer actually works. Let's break this down.
The whole mechanical action happens in a few really rapid steps. First, the operator presses the plunger, that's the tip of the hammer, firmly against the concrete surface. As it pushes in, a spring-controlled mass inside the housing retracts against the tension of the spring. Once it hits a very specific point, boom! The mass is released, it impacts the concrete, and then bounces right back. The distance that mass travels on the bounce is what we call the rebound number. There's this little rider inside that moves along a graduated scale, holding the reading in place so the operator can jot it down. It's elegantly simple, really.
But of course, here's where the physics throw a wrench in the gears. You can conduct this test horizontally against a wall, vertically downwards on a floor, upwards on a ceiling, or pretty much at any angle in between. And since you're relying on a bouncing mass, gravity changes the bounce. That means for the exact same piece of concrete, every different angle is going to give you a different rebound number. Because of this, you absolutely need a separate calibration or correction chart for every single angle you're testing at.
Okay, let's look at Section 4, variables and serious limitations.
So the really crucial thing to understand here is just how incredibly sensitive this tool is. Remember, you're only testing the absolute top surface of the concrete. That means any minor surface variation is going to wildly mess with your results. If the surface is even a little bit rough, or if the concrete's moisture level changes, the bounce changes. Literally everything from the type of coarse aggregate and cement used, the specific mold the concrete was cured in, and even natural carbonation on the surface will skew that rebound number. Even the rigidity of the concrete specimen itself changes the reading. It is a lot to account for.
And that leads us to Section 5, the final verdict.
Consider this stark number, plus or minus 15 to 20%. That represents the massive variation in strength estimation when using this tool. Think about that. Even if you're using a perfectly calibrated hammer on a totally smooth surface and calculating all the right angles flawlessly, your estimation of the concrete's actual compressive strength could still be off by up to 20%. In the highly precise world of structural engineering, a 20% margin of error on a load-bearing column, that is a massive, completely unacceptable gap.
This exact realization actually led to a major international survey by Rylam back between 1965 and 1967. And their consensus basically hit the nail on the head. The rebound hammer is fantastic for checking the uniformity of concrete, meaning you can use it to quickly verify if one part of a wall has the same general hardness as another part of the wall. But the vast majority of experts totally rejected using it for acceptance testing. It's just too unreliable for determining absolute strength. Bottom line, it's a comparative tool, definitely not an absolute measurement.
Which leaves us with this final thought to consider today.
If we can't fully rely on a surface hardness test to give us the exact structural integrity of the buildings we live and work in, what exactly is next? As our global concrete infrastructure continues to age, engineers are increasingly pairing the rebound hammer with advanced methods like ultrasonic pulse velocity, which actually shoots sound waves straight through the material. But it really makes you wonder, as our world gets older, what other non-destructive technologies will we need to invent to truly guarantee the safety of the built environment around us?